Hello and welcome to Toddcast number 60. So continuing on carbonyls, and just like the past Toddcast, we're going to cover a good amount of things that we've kind of seen before, but going to go a little bit slower this time. And going to revisit the same mechanisms we see over and over and over. So in this particular case, we are going to look at the conversion of a carbonyl, sigma bond and pi bond, to from a carbon to an oxygen, being turned into two sigma bonds. So we did this with acetal formation, ketal formation. So we're going to look at this more from an equilibrium standpoint. And so if we have an alcohol, so let me just revisit this, that acetone, if we treated it with, let's say, ROH under acidic conditions, if you recall, we will get still two bonds of O, but now there'll be OR and OR, known as a ketal. Okay, but what if we use water? Instead of an alcohol, if we have water, will it put two OHs on? So if I get rid of that R there and treat it with an H, then will I get OH and OH? So that's known as a geminal diol, geminal meaning twins. So the two H's are coming from the same mother, same carbon here. So the question is, how much will that equilibrium shift? Not the mechanism yet. We'll definitely do the mechanism, but we're interested in how much will happen. So if I have acetone with two R groups, acetaldehyde with an R group and an H, and then formaldehyde, just two H's. So a simple comparison. So two R groups on the carbonyl, one R group and one H on the carbonyl, and two H's in the carbonyl. If you have R groups, it ends up formation of a diol is relatively unfavorable. You're going to get 1% or less as the R groups get bigger and bigger. So with the R groups, because they can donate and stabilize the carbonyl is a little more favorable, and it stays in this form. Also, sterically, it's a little bit better. When I go to an aldehyde, less donation, the H cannot donate in to stabilize the carbon. So if you recall, there's hyperconjugation from the two methyl groups or inductive effect from two methyl groups, either way you want to look at it. Now when we only have one, it doesn't make this structure as favorable to stabilize the carbonyl. So you end up getting a little more of the diol. In this case, about 1 out of every 7. So 1 part of the diol, 6 parts aldehyde. And then when you have two H's, you have absolutely no donation. So the carbonyl doesn't get stabilized as well, and you end up forming predominantly the diol. Fun fact that was mentioned earlier, ends up with formaldehyde. Formaldehyde, even by itself, you don't even get that structure. You end up getting this trimer where the O of one formaldehyde attacks another carbon, kicks up an O minus, which attacks another carbon, which comes around and forms these three. So we have a C, an O, an H, and an H here, here, and here. So the formaldehyde doesn't even like to form a pi bond even when there isn't water. So no surprise that you end up getting so much of the diol formed. Okay, so we have these equilibriums. There's something to know that you can go through these diols, and it's going to affect the reactivity. Because for some like oxidation reactions, as we learned, the diol form is actually the one that gets oxidized, not the carbonyl form. So you need this equilibrium to go forward. So how does the mechanism work? As always, we have a base and acid approach. So let's consider base conditions first. Deprotonate, make, break protonate. It's going to be something along those lines. If I start out with something that's already deprotonated, then I take away that step. So deprotonate, done. Water's deprotonated to form hydroxide. Make and break, often done like an SN2 concurrently. So it comes in to make a bond, and the pi bond is broken. So make, break, last step has deprotonate. So it has it interact with water. This native comes in, deprotonates, and you end up with the geminal diol. So I've chosen formaldehyde. Again, I could choose anything. Could have put an R group on here. Could have done the ketone, but as mentioned, you have to worry about the equilibrium. So as long as we move formaldehyde, this equilibrium will go in the forward direction very much so. Acidic conditions. Under acidic conditions, again, the mechanism, you should just know this point, protonate, break, make, deprotonate. So we have our source of acid is going to be water. A lot of these reactions I'm going to do with water just because carbonyl chemistry can be done in hydrophilic or hydrophobic environments, but acid-based mechanisms are done more often in a hydrophilic, or in this case, aqueous scenario. This carbonyl, most basic site, is going to protonate. So it gets protonated. So protonate, break, form the carbocation intermediate, and make. I'm going to draw those two steps simultaneously. So break happens first, then make. And then last but not least, deprotonate. This water has to get deprotonated. Another water stone pair comes in, and you regenerate the original acid, and you have a geminal diol. So protonate, break, make, deprotonate for acidic conditions, deprotonate, make, break, protonate for basic conditions. Same mechanism over and over and over. So want to revisit the Ketal generation and do that same pathway, just make sure it's honed in. So first step, under acidic conditions, you can only get Ketal formation under acidic conditions. So if I had an acid, and in this case I'm using a diol, but I could also use individual alcohols, but we can end up getting a Ketal, which again still has 2 bonds to O, carbon bonded to O, carbon bonded to an O, just they're both sigma bonds. Mention that it was a so-called double ether when I was talking about it, because that's why it's so inert, but technically it's a Ketal. First step, protonate, second step, break, third step, make, last step, deprotonate. So protonate, we're going to pick up the H. Second step, form this resonance structure where it breaks. Protonate, break. This carbocation can be attacked, so one of these OHs can be either one because it's symmetric. And then finally, something comes in and deprotonates it. The something, I'm not going to be that particular because there's no way we can go swimming in the flask to know what's deprotonating it. But it could be this ketone, as that is the one that picked up the H in the first place. So another ketone doing its own mechanism can come in and pick this up. Whatever you put in there, that's fine. I'm drawing this just falling off because I don't know what picks it up. I do expect you to note that something has picked it up, but whatever you put in there just has to be reasonable. Could be the ketone, could be one of these OHs here. Okay, so protonate, break, make, deprotonate. At this time we have an OR, but we have an OH because that H, we have a hemi Ketal. So we have to keep going. Another round of all these. Protonate, break, make, deprotonate. So we've got to protonate again. I'm going to protonate here, although technically I could also protonate here. This wouldn't leave very well because it's primary, but if I protonate here, if this leaves, it's resonance stabilized and it's secondary. So this is a much better leaving group. So we're going to protonate this. I protonate here, it just goes backwards. So I protonate that OH to form water. Water is a good leaving group. Water leaves. So there's my break. This O, because it's so close, intermolecular is faster than inter. It can attack. There's your make. And then finally, this H can be deprotonated. And again, could be this species that deprotonates it, could be a ketone deprotonates it. I don't know, so I'm just going to send it up to this final product. But again, mechanism protonate, break, make, deprotonate, protonate, break, make, deprotonate. I am pushing this mechanism over and over and over because they do the same thing under acidic conditions or basic conditions. So just note this. Carbonyl mechanisms, if they involve a nucleophile, it's going to be very similar. Again, it's going to be protonate, break, make, deprotonate, or deprotonate, make, break, protonate. It's got to be one or the other. So Ketal formation, protonate, break, make, deprotonate, and you end up getting the hemi Ketal or acetal as it may be. And then round 2, protonate, break, make, deprotonate, you end up with your final product. Hydrolysis of a ketal is just the same thing, but run backwards. So if you start with a ketal and you're going to quench it with water, protonate, break, make, deprotonate, you end up with a hemi. Protonate, break, make, deprotonate, you end up with a final ketone again. So to regenerate it, you add water to push it, the equilibrium towards the ketone. To make it, you add the diol in the absence of water, and you push it in the direction of the ketal. So it's still an equilibrium. Everything's an equilibrium step except for the resonance, the few resonance structures. But hopefully this seems fairly straightforward. So we're going to do something called transesterification. Again, this is dealing with a carbonyl with a leaving group. And although this is aldehyde ketone chapter, I'm still a firm proponent of looking at these mechanisms applied to all sorts of carbonyls. So in transesterification, we do the same thing where we start with our original species. We'll protonate, break, make, deprotonate to get an intermediate with 2 OR groups and an OH. And that's going to undergo another protonate, break, make, deprotonate session, end up with a new ester. The reason this is important and why I'm pushing it is for some of you who go on to take biochemistry without taking additional OChem, this will become key because you will change this OR group from, let's say, a fatty acid just by itself, adding to glycerol. So if this OR is the end chain of the ester we're getting rid of, or OH we're getting rid of, or an O with some biomolecule we're getting rid of, and instead replacing it by putting on a glycerol, this is how you make cell membranes. This is how you make fatty acid triglycerides. The key thing here is that you can change this OR group into whatever you want. So this reaction is going to end up being really common in biochem. It's going to be, it's one of the things you probably learned is glucose transporters. You can move them through cell membranes. You have to do convert the glucose into a more hydrophobic molecule. So if you take some of the OHs, you bind through transesterification, you bind the OHs and turn them into an alkyl group. You can slip through the cell membrane and then you release them. So note that an ester and an ester, you go from an ester to an ester. So K equilibrium should be close to 1. It's a, I can't really call it a favorable, unfavorable reaction. It's something going back and forth. Transporters, because you need to put something on to help move a molecule across a cell membrane and then release it, those reactions almost always have K equilibriums of 1. So you force it, the glucose to bind, that long R chain goes across the cell membrane in this form, and then you can push it backwards because of the K equilibrium. So again, this is not necessarily going to be tested, but you have to know it, this whole process. So we're going to do the same mechanism, protonate, break, make, deprotonate. So here's my alcohol. Here is my original OR. So note, I'm going to just signify, this might be, let's say, an ethyl, this could be a methyl, and this could be like a glycerol or some longer chain. As long as the R groups, they don't have to be different, but we're just looking at this, paying attention to 3 different R groups just for identifying purposes. Okay, protonate. Perfect. Now we make pi bonds susceptible to breaking. Protonate, break, have a carbocation. Make, this new alcohol is going to attack in. It attacks in and forms this bond, and then deprotonate. So again, we have that species where we have the alkyl group, we have an OH that we formed, we have the original OR, and we have the new OR coming in. Again, protonate, break, make, deprotonate. So protonate this O again. Only this time we're protonating when we have one to leave. So this, apologize, that's the O we're getting rid of. Protonate, break. Going to make, and notice this again is a resonant structure. Single-headed arrow, and then finally deprotonate. Same mechanism. So protonate, break, make, deprotonate, protonate, break, make, deprotonate. So pushing this mechanism on you over and over and over so we just see the big picture of how all these things come into play. Again, because we're dealing now with a leaving group, this is technically not fair game for what we're doing in this chapter, but this will be useful down the road. So again, this whole bio push. major part of taking organic chemistry is so that you can be better suited to understand biochemistry, cell bio, molecular biology. The absolute best biologists are ones who understand the fundamental chemistry behind the biology they study. Be that person if that is your major. So examples you're going to see down the road, glucose could be an open chain, straight chain form. That's usually the one we draw in Fisher projection. So here it is, but it can also form a six-membered ring known as a pyranose. So just to keep track, I have carbon 1, 2, 3, 4, 5. This is why this OH is the one we consider for DNL, because this is the one that's going to attack and close the ring system. So this OH right here is going to be the sixth atom in the ring. So we're going to have a carbon, 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 oxygen ring. So if this O can come in and attack the carbonyl, we'll end up forming this cyclic. So because six-member ring, this is the magic one that has to attack in. So let's again just double check our carbons. Carbon 1, check. Carbon 2, check. Carbon 3, check. Carbon 4, check. Carbon 5, check. And then the O we added in right here is that O right there. So I'm going to perhaps put that in blue. What we formed is a carbon that has a bond to OR, bond to OH, a carbon and an H. So because it came from an aldehyde with a carbon and an H here and this H here. So because it came from an aldehyde, it's got to be an ACE of some sort, but because it still has this H right here, this is a hemiacetal. If you know about sugars forming polysaccharides or extended chains of sugar residues, of monosaccharide residues, you'll know that this linkage, this carbon right here, can form to another sugar to another sugar. You get what's known as a full acetal linkage. Hemiacetal is the individual one. The acetal is one that's linked from one sugar to another sugar to another sugar. So that's going to be the second one then. So here's my acetal coming up. So here I have my hemiacetal, and if I have two hemiacetals, so this one here, this hemiacetal, this OH can leave. So I've highlighted the OH here and the H here in blue, because that's going to be my side product, my water. But this hemiacetal here and this OH. So this is not going to be the exact mechanism, but basically that's what you have going on. It goes through, as you can imagine, a protonate, break, make, deprotonate, or if it's biological, instead of protonate, you'd be adding an enzyme. So Lewis acid, break, make, and then remove the Lewis acid. But I'm just going to say that's your general pathway to expect. Let me get rid of my writing here. These two come together. This is where we lose the water. You form what's known as lactose. So water is your side product. This is also why, and you probably have learned this in some bio classes, why when you break sugars down, you eat a starch, like crackers, for instance, it'll dry your mouth out because you need water to cleave that bond. So when you form it, you release water. To break it, you need water. Okay, so lactose is a galactose and a glucose. So galactosyl glucoside, as it's called. But what I'm most interested in is what used to be a hemiacetal in this form is now an acetal. So we call it an acetal linkage. And you still have an hemiacetal in this group. So this right here is an acetal. This is still a hemiacetal because that H right there. Okay, so naturally occurring ones. We just looked at lactose. This is a case where we have a glucose connected to a fructose. You'll note that in this one, this carbon right here is connected to an OR and an OR. So that's your acetal linkage. Over here, you also have this carbon, carbon number 2 of fructose, connected to an OR and an OR. So this is also acetal. Technically, this is a ketal. So for our purposes, I want you to call this yellow carbon an acetal, and this blue carbon a ketal because it came from a ketone. But when you get into biochemistry, they do not distinguish. They don't bother caring. They call everything acetal linkage. So they're going to call both these acetal linkage. And you may have even learned this is a so-called alpha 1,6 linkage because this is on carbon 1, this is on 6, and they're trans. And you may have learned this is a beta 1,2, or I'm sorry, not beta 1,6, but alpha 1,2 with respect to this one, beta 1,2 with respect to this one, because they are cis, the linking O and the CH2OH. That's for another time. That's either biochem or 311, you'll get that. So note that this over here is my ketal, and this over here is my acetal. So it has both an acetal and a ketal group. And then one more I want to bring up. This is what you'll find in blood types. So on the surface of a red blood cell, you have what's known as a glycoprotein, a protein that's bound directly to the surface. And on the end of the protein, you have glyco, or sugar, connected to it. Depending on what blood type you are, this marker will be slightly different. So this is a glucose with an extra addition called something called an N-acyl. This is a galactose, and this is a fucose. These three make up blood type O. Blood type A will have another galactose here. Blood type B will have another galactose here as well, but there'll be an N-acyl group as well. But blood type O, only 3 sugars, which makes it the universal donor. If you add this one into anything, blood type A and B have these same 3 sugars plus an extra one. So if you add this type O into A or B, you don't have a foreign body, so therefore the body doesn't reject it. If, however, you put A and B into O, so if you have an extra sugar here and you put it with somebody's blood type O, the extra sugar over here will be recognized as foreign and it rejects it. So O is a universal donor because it doesn't have the 4 sugar. It has the 3 that are common with all of them. So it can be donated to anybody. But blood type A and blood type B have a 4 sugar that cannot be donated to blood type O, which only has 3 sugars. Not to teach a bioclass in the middle of OChem, but still find this pretty interesting, how these things tie together. The linkages. We have an acetal linkage to a protein, carbon with 2 bonds of O. We have an acetal linkage from the glucose to the galactose. So notice this looks an awful lot like lactose that we just did. And then there's one last group here, which is also an acetal linkage because it comes from an aldehyde, aldehyde, and aldehyde. So acetal linkage, acetal linkage, acetal linkage. So there's 1 acetal, 2 acetals, and 3 acetals. So you're connected by these acetal linkage. So C, I put an A not to say acetal, but this stands for anomeric. Another word you'll learn down the road, but alpha and beta anomers simply means the chirality of this anomeric carbon, whether the O is pointed down, like it is here, in an axial orientation, or whether it's up in an equatorial orientation. Okay, lots to cover. Realize there's probably been a little bit of bio overload, but that's where this gets sort of interesting. So if you're moving on to biochemistry, learn these, how they apply to bio and the utility of them. If you're moving on with OChem and worry about synthesis, know there's a whole sea of reactions, and the carbonyls do basically the same thing. You have to consider, do they have a leaving group or not? And are you adding a nucleophile or a base to them? So hopefully this is summarizing fairly nicely. And I will see you at the next podcast. So have an absolutely wonderful day and see you soon. Bye.